Good morning. Today I try to explain you about a method, a new method maybe, that will be compatible with the online and in real-time blood oxygenation mapping in the optic nerve A, in the little space of the optic nerve A. In fact, the current presentation proposes a new method to estimate blood oxygenation for a limited number of absorption measurement of few specific wavelengths in the visible spectrum. To validate the new model for blood oxygenation computation, the spectral reflectometry absorption data collected with the multi-channel technology instrument from a single point of the optic nerve papilla was used. In fact, we use this technology that I proposed in 2009, the multi-channel. In fact, we take one measurement in one specific area of the retina, is at one point. The image of the fundus is projected here at this mirror. Here we have a pinhole with an optical fiber that catches the light, come in the spectrograph, and each point is represented by 200 measurements from 400 to 600 nanometers. It's a lot of wavelength. The black point here on the image represents exactly the point where the measurement is made. But let's be experimented to see that. That is the experimental setup. Exactly. We change the parameter to fit. After the computation of 4 parameters here, we check if the data here fit 2. Okay. We make two different computations. It's not only one. Because if you make only one, you can obtain a fit with some differences here, but that can to have error in the blood oxygenation. I propose another method to compute blood oxygenation from this equation and to separate what is representing the blood absorption and what is representing the eye media and scattering. And in the first step, we propose to obtain this equation only for the isosbestic point, because if you use this equation for isosbestic point, it's not possible to differentiate oxygenation from hemoglobin for oxyhemoglobin. We propose that for only isosbestic point. In this case, the M1 and M2 become to be another parameter, MH, that represent the total hemoglobin. And here is the spectral absorption from hemoglobin and oxyhemoglobin, because it's the same for isosbestic point. We separate the 10 and we apply the logarithm from this function. What is represent this expression is only an equation for the first degree, is a line. Exactly. The 10, where the A here representing the slope is exactly the end parameter from the equation in the heart. This is a representation from this equation, where here we have the logarithm from absorption minus 0.15. That is a parameter that we modelize to obtain a line. And that is the equation of this line. The equation of this line we have minus 2.7 represents the n parameter, 7.8 represents logarithm of M3, and 0.15 there represent the MH, the total hemoglobin method. In fact, by this method, we'll be able to separate hemoglobin from other absorption in the spectral function. If you use this method for all the data, we obtain a similar data is the same average, but is a little more variation. I don't know exactly if this variation is only because we use here is an example with 8 wavelengths. We have 5 isosbestic points and 3 non-isosbestic points. I don't know exactly if this variation is from only 8 wavelengths or represent a more sensitivity method. The next step we explain this one. In conclusion, the absorption value at the isosbestic wavelength are optimal to differentiate the blood oxygenation, the blood absorption from scattering and ocular media absorption in a reflectometric function from the optic nerve papilla. A minimum of 3 absorption values at 3 different isosbestic wavelengths will be necessary to apply to obtain this collinear method. 2 points are all of the time in the line. 3 points. You need to be sure there are not noise in your data, because 3 points is very easy to put in the line by this method. If there are not noise, maybe to be. Second, a single absorption value measured at the wavelength where the hemoglobin and oxyhemoglobin extinction coefficient present a local maximum difference will be adequate to differentiate the hemoglobin for oxyhemoglobin. Theoretically, with 4 wavelengths, 3 for isosbestic and 1 for non-isosbestic, for determinist data with non-noise will be enough to compute the blood oxygenation that correct for optical eye absorption and scattering. But that is good for optic nerve right now. I don't know. It's necessary to check what's happened with the artery and vein. After. The method. What is the method to obtain a multispectral imaging? There are a lot of methods after that, but it's very important to obtain, for example, the image at very, very, very spectral data. For example, with the bandwidth not more than 2 nanometers, because if you have a very, very large spectral of the light in the eye, you decrease the sensitivity of blood oxygenation measurement. Okay, if you have question.